In this video, I want to prove a major theorem about the degrees of polynomials. And in order to get started, I want to look at what the definition of the degree of a polynomial is. So we're going to let R be any ring, and then R of x, R square bracket x, is the ring of polynomials where the coefficients are drawn from the ring R. And if I let P of x be a polynomial over R, and P of x is written as a sub m times x to the m plus a m minus 1 times x to the m minus 1 plus all the way down to a1 times x plus a0, then the degree of P of x is going to be m as long as we understand that this particular term is not equal to 0, and this is the largest power of x with a non-zero coefficient. Now, the tricky part is really when we start talking about degrees of constant polynomials, and that's what I really want to review with just a little bit of detail. So if I happen to have a polynomial, I'm just going to call it g of x, and it is identically equal to a sub 0, where a sub 0 is an element of my ring R, then one of two things happens. The degree of g is going to be equal to 0 if and only if that constant is not 0, and the degree of this polynomial is going to be set to minus infinity if and only if that particular constant is equal to 0. In other words, the degree of the 0 element inside R square bracket x is defined to be minus infinity. Well, now that we've reviewed some basic facts about degrees of polynomials, let me state the theorem that I want to prove. So the theorem says this. Let's let R be a domain. Now that means R has no zero divisors. And then what I want is I want to let P and Q be any polynomials in R square bracket x. Then the degree of the product, P of x times Q of x, is just going to be the degree of P plus the degree of Q. And this is not an unexpected result if you think about how polynomial multiplication behaves inside of high school algebra classes. And inside high school algebra classes, the coefficients are always being drawn from a field, and fields, of course, are special kinds of domains. So the proof is going to be fairly simple, although we do want to break it into two cases. And I'm going to call the first case that one of my products, either P of x, is identically equal to 0, or Q of x is identically equal to 0. It could be the case that both P and Q are identically equal to 0. But in this case, then what I know is that P times Q is also the 0 polynomial, so the degree of the product is going to be minus infinity. And if I think about the degree of P of x plus the degree of Q of x, well, one of these two things, either this guy or this guy, is minus infinity. Possibly both of them are minus infinity. So this is going to essentially break down into either minus infinity plus a constant, which will be minus infinity, or it'll be minus infinity, which is just minus infinity. So if either of my polynomials is the 0 polynomial, the theorem works. Well, now let's look at case 2. In case 2, I know that both p of x and q of x are non-zero polynomials. And what does that mean? That means that I can write p of x as some leading coefficient, I'm going to call it a sub n, times x to the n, all the way down to its constant term. Q of x is equal to, say, b sub m times x sub m, plus all the way down to its constant term. And it's worth noting that the n or the m might be equal to 0, and we might get a constant, but that's not a problem. But once we have this, I know how to find p of x times q of x. That's just the first polynomial times the second polynomial. And when I start thinking about how polynomial multiplication works, I know that the product is going to be done by doing the distributive law. And so the very first thing that I'm going to get inside my product, and the highest power of x, is going to be this leading term times that leading term. So the biggest power of x inside the product is going to be an x to the n plus m, and its coefficient is going to be an times bm. Plus, and I'm going to say there's a whole bunch of terms that I don't care about. The constant term at the very end is going to be a0, b0. But once I know that this is what the product is going to look like, I can say some very important things. The degree of the product now is clearly going to be n plus m, and I know that because an times bm is not 0, since R is equal to a domain, and hence has no zero divisors, and I know that an is not 0, and I know that bm is not 0. So that's what tells me this leading coefficient here cannot be equal to 0. And that's what tells me that the degree of the product is indeed going to be n plus m. So what we've got now is, let me get my right color. So the degree of p times q is indeed n plus m, but n is just the degree of p, and m is the degree of q, and so that ends the proof. But there's something that I want to point out about this proof, because we get a corollary out of this proof, and it comes from this part of the proof. So I kind of want to point something else out as a corollary. If our ring of coefficients is a domain, then it turns out that the ring of polynomials is also a domain. And the reason why is the proof that we just did. And I want to, in the proof that we just did, and I'm going to go back to, we assumed that we had, let's get the right part, we assumed that we had two non-zero polynomials. And we showed that the product of two non-zero polynomials was a non-zero polynomial. So I want to get that idea written down for the proof of my corollary. So in the previous proof, we showed that if p of x was not equal to the zero polynomial, and q of x was not equal to the 0 polynomial, then p of x times q of x was not equal to the 0 polynomial. And that's enough to say that r square bracket x has no 0 divisors. And that says that r square bracket x is a domain. And that ends this video.